The Controller Area Network, or CAN, has been widely used in automotive applications for many years, but has recently become popular in non-automotive applications such as machine control, home appliances, and building automation. What makes CAN so attractive? Well, let's take a look at the various types of serial communication channels that are available to embedded developers. First, there are synchronous transmissions such as SPI and I2C that are capable of high data rates over short distances, making them ideal for on-the-board communications. For off-the-board communications, asynchronous transmissions such as UART, LIN, CAN, USB, and Ethernet are all available. UART and LIN are good low-cost options, but have poor noise immunity. And while USB and Ethernet have good noise immunity and high data rates, they are also expensive. When cost is a factor and noise immunity is important, CAN is a great fit. Let's take a look at a security system application example. The system contains a main control unit, zone sensor, door sensor, alarm, and keypad. What type of communication is best for this network? First, USB and Ethernet are clearly overkill for this application, and so they can be removed for cost reasons. If point-to-point or single master bus topologies were used, the wiring would become convoluted and time-consuming. This rules out SPI, UART, and LIN. Having a multi-master bus topology simplifies the wiring needed, and so leaves I2C and CAN for consideration. One of the key differences between I2C and CAN is noise immunity. CAN uses differential signaling and has built-in error detection, giving it excellent noise immunity. And since noise immunity is important in security systems, that makes CAN the best communication choice for this network. Another benefit of CAN is its ability to do real-time control. CAN's ID field can be split into user protocol fields such as group priority, function, and device address. This means that in our security system example, when the door sensor detects an open door, it can send that message to the main control unit with critical priority, thus taking precedence over other messages on the bus. The main control unit can then send a message to the alarm, also with critical priority, and to the keypad with lower priority. The ability to assign different priority levels on a CAN network enhances real-time system control. So now you want to use CAN, and the question is, how do you pick one? There are 3 different types of CAN controller implementations. In a basic CAN implementation, there are 2 to 3 mailboxes, and much of the filtering needs to be done in software, all of which results in high loading on the CPU. Full CAN implementations include 16 to 32 mailboxes and integrate hardware filtering. This reduces CPU loading. And to even further reduce CPU loading, full CAN plus FIFO implementations integrate FIFO buffers for efficient processing of back-to-back messages. With 32 mailboxes, 8 acceptance masks, and optional FIFO mode, the RX CAN is a full CAN plus FIFO implementation, ensuring autonomous CAN processing with data rates up to 1 megabit per second and minimal CPU loading. To simplify system integration, RX CAN includes special test modes for listen-only and loopback. Renesas provides free CAN middleware with an easy-to-use API, and CAN support is also available from the extensive third-party RX ecosystem. With RX CAN, it's easy to create a scalable, real-time network which has excellent noise immunity, making it suitable for applications where safety is an important factor. To get started with your CAN development, visit our website where you'll find a handy product selector which will help you determine the RX CAN device best suited for your application. And to learn more about how to implement CAN using an RX microcontroller, Renesas Interactive provides a wealth of informative courses.